Hi, I'm Liz Larsen. I am the lead design engineer and owner of LTX Industries. We are a Denton-based company that produces specialty electronics for video artists. I'm also a graduate of the RTVF program here at UNT in 2006, and I am full-time staff at Clear across in Chilton Hall. But I guess I'm going to give you a brief history of how I started doing this and why. In 2007, I was along with several others, some of whom are in this room right now, very involved in participating in the local arts and music scene here. I would characterize what we were interested in doing at the time as very antagonistic to more mainstream movements and small performance art and that kind of thing. We were interested in sort of emerging new media art and internet art, but I think we're also wanting to make art that was critical of it. And at the same time, there was a renaissance in analog audio synthesis technology going on, and that kind of implied sort of this new frontier that was based on going back into time and exploring sort of a parallel timeline of technological development. I think we're so used to standing on the cutting edge of what's next and what can technology do that hasn't been done before and is new, and sometimes that progress evolves so rapidly that that there are things left unfinished because something newer came along. So so I think at the time, with my interactive programming background and film background, I was interested in electronics. I was interested in finding my own little pocket universe to explore as far as all of this goes. Exploration was an important theme of that. And I think we like the idea of creating kind of absurd devices that shouldn't exist, that don't have a financial, they're not designed to make a whole lot of money or have a big user group. It's designed to exist within the scope of a very niche user community. Jonah Lang, one of my main collaborators in those early times, in 2007, we were very much builders and project people. We like building things. We were interested in the idea of functional devices as art, or something that works. So we found we became exposed because we had been getting into electronics, and we got a bunch of old video gear and started researching from there. We discovered kind of the video art scene of the 60s and 70s, and were immediately inspired, because here is a whole community of very interesting, forward-thinking devices for their time, and they had kind of all the people that were doing that kind of work. Either the devices were just too expensive to sell to more of a common artist community at the time, or computers kind of distracted everybody away from it. But we had found this little pocket universe that we wanted to explore. So over the next few years, worked very hard on it. I teamed up with an engineer in Sydney, and who kind of served as my electronics mentor. and there was several years of very rapid development. We started selling the modules, and we're very interested in everything being as accessible as possible to, because we were creating tools specifically for artists. Like, we could assume that anybody buying our tool was going to be using it for the functional purpose of creating artwork. Like somebody might buy a paintbrush to paint a sign, but they wouldn't spend a whole lot of money on a paintbrush unless, I guess, they really liked making certain kinds of signs. I don't know. But so we wanted, knowing that our customers were all going to be artists, we wanted to build a community, and we wanted it to be as accessible as possible. And now there are over 200 users of the system worldwide, which is big for something like this, I think, and it's still growing. All of our the first 20 or so modules I designed were more based on functional utility blocks, like that you'd find in an audio synthesizer, like a oscillator or a VCA or a mixer. And it's because we wanted to create the building blocks from which you could explore more complex processes with the analog video signal. And now it's kind of taking a focus on more integrated, creatively focused devices, such as this is our new module here. Visual Cortex is kind of a mini video lab. It can function as like an input and an output. The key creative, exciting point of an analog system like this is most video broadcast devices aren't designed to turn things that aren't video signals into a viewable signal or color signal. And then people exploring, modifying existing video devices through circuit bending or modifications it can do interesting things with the signal, but they don't have total control over whether the signal remains viewable or, and so having an interface, just the basic interface of being able to plug anything you want, any electrical voltage in, and that becoming part of the video signal without destroying any displayability of it is kind of just opens up a whole new world that there wasn't anything really designed to do that. So this module, you can get, video comes in via standard RCA connectors, and it's all old school NTSC PAL or component video in the same timing formats. And once it comes in, then it's patched around with 3.5 millimeter cables. And there's control voltage inputs, there's signal inputs, and it's a very kind of, the voltage standard is all DC voltages. It's very universal, so you could plug a gate pulse from a sequencer and turn that into video. You can turn audio into video, and you become really aware of how, with video, with analog signals, they only exist in the present, so you don't have like a frame of data full of pixels to modify. You have one pixel that's moving really, really fast. And so if you intersect that pixel, one pixel that's moving really fast, your eye sees through persistence of vision, interprets that as a still image, but it's really not. It's just an illusion of a still image. So when you overlay audio with that, as the pixel moves and the audio waveform moves in time, you can visualize the audio on a screen. Like, like right here, this is a self-resonating filter. And you can see as I adjust the frequency of it, higher, we're seeing more lines. And as it gets closer to a multiple of what's the video's frame rate, which is 29.97 frames per second, then you see the lines move slower or up or down relatively to that. But so if we're seeing 8 lines, that's 8 times the frame rate. or about 150 hertz. So you can use oscillators, and you can synchronize them to the video display in different ways. And then there's complex linear mixing of color channels. Like I know a lot of audio engineers will record into a digital multi-track, but then mix down using an audio mixing desk or an analog mixing desk. And because you have all the analog bandwidth to work with, when signals are summed together, there's a big difference between a digital composite versus the fluidity of two voltages being added together where there is no real resolution other than the bandwidth. So you can get, I don't have a big system with me today or time to show off any like real complicated stuff. But this module has, basically what's going on right now is I've got the output section of this module patched into our projector. And I'm generating a color field here. Looks like we're maybe seeing a little bit of weird color balance in how it's translating to the projector, but that's okay. These color controls are generating the color field, and we could fade back and forth between an A channel and a B channel. We can also use a ramp waveform to make the same movement, and this happens via really high speed voltage control. So here's a signal that's a horizontal triangle wave that's synchronized to the vertical axis of the display, and a vertical triangle wave that's synchronized to the other axis of the display, summed together, and then going into green creates a diamond shape. We can mix that to different colors. Can key it out to create an actual diamond. We can change the slope of the ramp waveforms into different basic shapes. And this is all cool, but where it gets really interesting is that you can, this is all kind of, I mean, the way that we design is looking at older broadcast devices and all of the hidden connections that you don't have access to, or the things that they're not designed for. You make those all accessible so you can insert other signals there. So you can use like a camera to modulate an oscillator, or you could use an oscillator to modulate the key threshold over an external video feed. I guess the best way to kind of show a range of outputs so that there's something visual attached to this is maybe if we pulled up a YouTube clip of a previous recording. Is that something we can do? But that's the basics. Yeah, but search for LZX. It's at youtube.com/LZX Industries. Go to the channel page.
Up here?
Yeah.
I've
Yes. And the second video there, here's some recordings I made using this module and then one audio oscillator and a Korg MS-20 Mini. I recorded the audio from the synthesizer as I was using its control voltage outputs and kind of patching them into different colors or parameters. Maybe try refreshing. Does anyone have any questions in the meantime? Yes?
Did you look at Steve Beck's designs to base the things initially?
Yeah.
That's the one I knew from back in that.
Yeah. Beck had the direct video synthesizer, the DBS. And he and I have exchanged emails a couple times. But that is probably, there were very few truly modular systems. I mean, there was the Sandine image processor. And the Beck direct video synthesizer, and I think Stephen Beck did a lot of, he did some performances with, who was it that was playing the Buchla along with him?
Well, I saw him do it with Alan Strange a few times.
Oh, wow.
Susan Ciani one time. I'm from the San Francisco Bay Area.
Oh, okay. So, yeah.
That was really cool stuff, and this really reminds me of his things.
He had this concept of color chords, that which is basically a matrix mix between figures, video figures, and red, green, and blue channels going to an output. And this was one of the few systems based on kind of like a matrix. I mean, there was only like 3 systems to compare with, but probably the most, one of the biggest influences on the design of my system, for sure.
And wasn't Dean Sandine and that group, Grass Valley group, also were doing some things?
Yes, Dan Sandine. He designed, I mean, his documents were the most inspirational to me when I started this, because he released, he was working for the Chicago University. I always get the names of the Chicago universities wrong, so I'll try to say it. But
I think he was at Northwestern, but I
okay.
could be wrong.
This was the early 70s. He developed a video version of like a Moog synthesizer. So it had kind of more traditional synthesis elements, and it was truly modular. It's probably the only one system that was modular in the sense that there were actually separate, electrically separate modules. There were plenty of like patchable systems or systems that had separate functions on one big panel that were modular in that way. But he's a really sweet guy. I met him in 2011. I did a workshop in Chicago.
Oh, cool.
But he loves how small this is.
Is that Eurorec size?
Yes, it is.
Oh, that's cool.
So you can house the modules in the same cases and power supplies as the hundreds of amazing modules that all the audio guys are doing.
Should we go ahead and play it?
Yeah, go ahead. somebody who can play a synthesizer over. Go ahead and pause that. I'll play that one in the upper right corner. One kind of subset of video art. What we just saw was kind of what I'd call direct video synthesis, which is what Stephen Beck came up with that term. It's the idea of like applying signals directly into the video raster. This is a different method. It's using the same similar kinds of signals, ramps and oscillators, mixers and VCAs, but it's driving a XY display instead of a typical television. So on a television, the way that the beam moves across the screen and the order that things happen in is fixed. So it starts in the upper left and it moves and it creates scan lines all the way down. Whereas on a vector display, you're able to move the beam arbitrarily in to any spot at any time. So you're able to morph the geometry of the image, which you aren't able to do with a typical raster display. And this is there's a video game console in the early 80s called the Vectrex that incorporated an XY display. There was a kind of a hacked black and white television. I got one of those and I tapped into the driver board for the monitor, and this is just plugging signals from the video synth directly into the monitor on X, Y, and Z channels. But this is noteworthy because this is the effect everybody wants to do, because this is very difficult to aesthetically recreate on a simulation, on a software simulation. Because there's so much, because it's just a beam moving. There's no pixels, there's no quantization of the outgoing signals. And since a line that you might be seeing there is like happening sub-pixel or super pixel fast, like multiple times inside one pixel, the processing power to kind of simulate it and get all the effects of the glowing monitor screen is very difficult. So, this is the kind of thing that gets a lot of people interested in what we make. And I guess we should show an example of like processing an external video. If you want to cancel out of this, and we'll pull out one more. If you can go to the channel page down there at the bottom. Go to videos, see if there's something good here. Not really. I guess I've uploaded mostly.
Sunrooms.
Yeah, that one's kind of boring. Go up. I guess we can show the talking Bat Boy patch. If you go to the NYC workshop on the left there. Click on that.
Sorry, the front? No.
That one, yeah, that's good. This was at a workshop at NYC in New York in 2012, I think. It was 2011. If you want to skip to the end of this video, there's a talking Bat Boy that's pretty sweet. There it is.
Goodbye, sweet world. My time here was brief, but I learned many things about you.
I mean, it seems simple. It's just a bunch of video synth nerds seeing how far they can take it. Because that's a Bat Boy made all with analog waveforms summed together and several different keys to create the composite shapes. That was a fun time. Okay, cancel out of that. If you go ahead and close out of that video. And the one there in the middle, because y'all want to see this. Vector rescanning experiments towards the bottom. If you want to, this is my oscilloscope playing Casablanca through the video synthesizer. It's more of the vector type stuff, but in the last example it was just waveforms being creating the image, whereas this is a technique known as rescanning, and this goes back to radar imagery in the 40s and 50s. They would use XY displays like this to display sort of topographic data. And then in the 60s and 70s, there's the Scanimate system, was that analog animation system that made like all the Super Bowl commercials, you know, that were 3D in the pre-computer age. So the way to do 3D animation with an analog computing is with an XY monitor, so you can morph things around just by changing their offset and amplitude. But in this clip, it's similar to the rescanning from the Retro video synthesizer, which is another 70s device. But what's happening right now is I'm recreating the raster on a vector monitor by driving the X with a ramp waveform that's synchronized to the video source, and then the Y with another waveform that's synchronized to the video source's frame rate. And then the Z-axis is just the brightness, and that's being sent the actual video signal. So when you don't do anything weird to it, it just allows you to watch TV on your oscilloscope. But when you start adding the luminance information of the video in with the X and Y ramps that you're sending out, you get an effect called vertical or horizontal displacement. And then when you use a bunch of oscillators to modulate the amplitude and sum in with those signals too, you can have lots of fun. Okay, I think I'm done.